with countless smart objects being deployed for various vertical applications, we expect to make them easy to use, maintain, and diagnose, as well as reliably operational in a manageable way. We'll begin by exploring the basics of device management, including the architecture, key functionalities, key standards, and the protocols. Then, we'll cover the representative standards for IoT device management, LightweightM2M and 1M2M. I'll demonstrate how to build solutions based on these standards and how to use the commercial IoT platforms. I'm excited to share that with you now. To do the exercises in some demos, it's also helpful to have some Java programming knowledge, but it's fine if you don't. You can follow along to watch the demos. If you need to know more about Java programming fundamentals, there are many helpful courses on the library, such as Java Essential Training for Students. For the networking basics for IoT, you can check out my course on IoT Foundations, Low Power Wireless Networking. You can download them to your desktop. Included with this course are a few Java projects that will walk you through the software platforms built upon the device management standards. They will help you understand the concepts introduced in this course and get some hands-on experience for building your own solutions. These projects are written in Java and can be compiled and run with Apache Maven across platforms such as Windows, Linux, or Mac OS X. In this course, I will use Mac OS X with the JDK 1.8 and Maven 3.5, as well as Eclipse IDE for Java developers. I will then use the terminal to run the shell commands, Eclipse IDE to edit some source codes, and a web browser to show the web interfaces of some demos. I have included more specific instructions in the README file. If you don't have access to the exercise files, that's okay. I encourage you to still follow along as we go through the course. Now, let's get started. Increasing number of IoT devices deployed in our lives for a broad spectrum of applications. Some of these applications are for the comfort of our lives. Some applications are for mission-critical tasks in industrial environments. Some applications are used to improve the agriculture and to protect our environment. The applications are just a limitedness, and it may feel like when we talk about IoT, we may get lost in the possibilities. What will not make us get lost is grasping the enabling technologies that all IoT systems will need. Device management is one of such important technology enablements that IoT stakeholders, innovators, and makers need to know about. To understand it, let's take a look at what IoT system will look like. Almost all IoT systems need to be deployed in the field and scale. The meaning of scale is multifaceted. It can mean the scalability of our working system deployment in terms of the IoT devices. It can also mean it's scalable enough to accommodate the handling of data, services, and users. For example, we may have a large-scale IoT system consisting of hundreds or thousands of geographically distributed sensing devices, able to talk to each other and to do some application-specific tasks. For example, to facilitate operations of automation control processes in the factory or facility system, to monitor energy consumption in an office building, to manage crops with temperature and soil moisture data sensed, or to allow vehicles on the road to transmit data for remote diagnostics and emergent responses, just to name a few here. All these real-world IoT applications come with some practical operational challenges. For example, to make the device configuration remotely and autonomously, update software for bug fixes or improvements, retrieve device status and location, and set some extra custom metadata for additional purposes. All these challenges belong to the domain of device management in IoT. A device management solution can provide manageability to a scalable IoT system deployment. This is too generic still. So, in this course, we use the definition of device management given by the Open Mobile Alliance, where the device management is defined as providing remote device manageability to connected devices, such as provisioning, configurations, and updates on firmware, status, and diagnostic information. Centered on this definition, device management allows third parties to carry out the difficult procedures of configuring devices on behalf of the end users. Some typical third parties are operators, service providers, or corporate information management departments. Since the increasing number and kind of devices in IoT introduce new challenges that the traditional technologies cannot solve well, IoT device management requires new solutions. Let's see some of the main challenges faced by IoT devices. First, there are various types of IoT devices where many of them often have limited resources and capabilities in a network with a limited bandwidth. Second, most of the IoT devices need to perform the machine-to-machine communication to exchange data with wired or wireless connectivity options. In this context, the connected devices can be called IoT devices or M2M devices, where we can think of M2M devices as a subset of IoT devices as well, which often has less powerful hardware resources than a regular personal computer, for example. In this course, these two terms are simply used interchangeably. Third, most of the time in IoT, we don't need much manual intervention, so the management procedures may need to be done efficiently, autonomously, and securely on one or multiple devices. Fourth, we often need a scalable setup when it comes to IoT device management. For example, we need to manage a large scale of IoT devices across communication networks and platforms. And last, the device management solution needs to be able to handle the manageability in the entire life cycle of an IoT device. To summarize, there are the advantages can utilize a device management solution to many applications in various industry segments. I would like to talk about several use cases here. In a smart home scenario, different connected objects such as connected appliances, lights, security cameras, and thermostats can be remotely managed. Take the smart appliances as an example. An M2M service provider can manage the appliances in different ways, such as checking their diagnostic information regularly reported from devices, initiating the provisioning of the security credentials and policies to prevent appliances from unauthorized access or operations, and configuring them to automatically download and install the latest firmware images for improvements and new features. Also, it can be used in public services in a smart city. In a smart city application using occupancy sensors to manage citywide parking spots deployed by an M2M service provider. The service provider can bootstrap the sensors, configure them with security credentials and identities, check the occupancy status reported by the sensors, and update the firmware. With the data collection capacity, a device management solution can be extended to be used for vehicular information collection. For example, a car configured to regularly report its location to a central server can be tracked when it's stolen. At that point, we most likely need to use the underlying network services from a cellular operator. In an enterprise building automation application, the connected HVAC devices need to be managed for diagnostics and to report the electricity usage data, for example, for energy consumption optimization. In a device management solution to manufacturing automation systems, the M2M devices in terms of their hardware capabilities and network connectivity options. But why we need to classify manageable devices? First, a classification can help group the seemingly unlimited number of IoT devices into a manageable number of classes to enable the analysis for reusability and handling for new types of devices. It matters to M2M service providers and stakeholders in a DM solution in an IoT system. Second, classifying devices can help us access a DM solution to an IoT system, as devices being managed are the major objects in the system. The assessment is multifolded, including infrastructure assessment, security risk assessment, etc. Third, it can help with the design of a suitable and efficient solution. For example, we don't want to apply a DM software framework on a device with very constrained compute power and memory, or applying a DM protocol in a constrained network requiring excessive bandwidth beyond its capacity. It can also help with the deployment and optimization strategy of a DM solution, as the devices being managed need to be deployed in an optimized setting based on their capabilities and functions. Let's begin by looking at a popular device classification by hardware capability. An IoT device, which is an embedded system essentially, can have different resources in terms of the following attributes. Compute power. A device with an 8-bit MCU has less compute power than the one with a 32-bit MCU. Also, this compute power affects the algorithms, such as cryptographic methods we use for security in a DM solution. Storage. For example, a device may have a tenth of kilobytes of RAM, or they have hundreds of megabytes of RAM. A device having persistent flash storage allows us to provision it with security credentials easily. As another example, if a device doesn't have the persistent storage, the device may not be able to update firmware remotely. Network connectivity options. For example, some devices have LTE or LoRa radio interfaces, some have Bluetooth or Wi-Fi radio interfaces, and some have Zigbee or Z-Wave radio interfaces. Sensing capabilities. For example, devices may have a mix of sensors such as GPS, accelerometer, gyroscope, temperature sensor, light sensor, etc. And finally, energy source. For example, some devices are powered on a single battery or by energy harvesting methods, and some devices, such as gateways, are often mains powered. For devices with mains power, we may run a full-fledged DM software framework integrated with other software. However, if we manage resource-constrained devices connected in a limited bandwidth network, we may need to use a piece of DM software that is efficient in power consumption and to exchange data with other devices using a network protocol using compact binary packets. These capabilities are important for device management protocols running on top of manageable devices in order to fit into them. If we look at this classification we'll use in this course, in a hierarchical diagram, the devices can be generally classified into two classes, which will be used often in the device management protocols also. One is resource-constrained devices, with limited hardware resources we've mentioned, where we can see some example devices here shown on the right. And the other class of devices is called regular devices, including regular computers and single-board computers. There are some other classifications that can be helpful as well. First, devices can be classified by communication modes supported, where devices can only do unidirectional communications, for example, either sending data to a server or receiving data from a server. For example, a weather sensor may only transfer temperature values to a server. A device can also do bidirectional data transfer to be able to send and receive data in two ways. For example, if a weather sensor needs to be upgraded to the latest firmware, it has to have the bidirectional communication capability. In the IoT system, we can group devices by their functions. One way of doing this is based on their role in IoT system architecture. In this sense, they are M2M gateways, M2M devices in the field, and proxy or relay devices helping relay the message between the first two types of devices. IoT devices. A general device management solution needs to work across IoT platforms, such as hardware platforms, like single-board computers or other embedded system boards, and operating systems, such as general-purpose and embedded operating systems. Note that it's possible to have a DM solution without an OS. Let's look at architecture for a DM software solution first. We can implement everything regarding DM for each device platform, which is difficult to make the solution scale easily. Or we can decouple some high-level DM functionalities from the device-specific hardware and OS operations, as shown in this diagram, as a first step to make the DM solution work across different platforms. Following this approach, we can consider the DM solution as an end-to-end solution running on the computers or devices across a communication network, mostly IP-based network, such as Internet, which can be seen in this diagram, where the essential parts are shown here, such as DM application endpoints, message transfer protocols, and device platforms, which indicate a specific OS and hardware platform. We can view this architecture into three layers, where we consider the DM applications implementing the DM functionalities are put into the DM application layer, the message transfer protocols, which provide direct message transfer services to the DM application layer, are at the communication protocol bindings layer, and the other underlying network services and the connections are put at the underlying communications network layer. Most DM solutions adopt the client-server model, which means a DM application usually has two entities. The first entity is the DM software agent running on devices being managed as DM clients, and the other entity is the DM central controller running on the local or remote DM service endpoint as DM server. We can have multiple DM clients and multiple DM servers. And in this way, this end-to-end solution is flexible to fit many use cases. Let's see how a DM client application called DM agent, for short here, interacts with the DM server application. The DM agent can manage the resources on devices as shown here, virtualizing the devices in terms of a structure of essential resources in terms of metadata and digital objects regarding the management of IoT devices, such as device info, firmware version, location, etc., where a DM server application endpoint can access them remotely. The DM agent also does interfacing with the DM server. For example, if your application is running on a Linux OS, the DM agent running on top of it, considered as software agent, which can take remote commands, invoke OS-related commands, and interact with other DM entities across an internet. For example, if the DM agent is receiving a firmware update command from a server, it will securely identify and download the new firmware image, invoke a series of OS commands to do the update operations, and then send the results out to indicate whether the operations is successful or not. This way, we can see that the DM agent provides an interface to do the operations on a device, and at the same time, interact with other entities involving in a DM process. We can easily implement or use the same DM agent with a different OS. For a DM solution implemented with Java or Python, you can easily expect that to work on many platforms. We'll see standard-based device platform agnostic DM solutions implemented with Java later. The DM server application endpoint, as a controller, performs the DM-related operations in a centralized way, providing DM service amongst other services on a remote server or on the cloud. Therefore, if putting things together, we have a general architecture for a DM system, although there can be other components added, such as security gateways sitting on or in between the end devices and a DM server. The M2M end users who can be the subscriber to the DM application services based on the basic DM services. With the general system architecture for a DM solution, there are some key actors we need to understand. They are application service provider, who provides services to the M2M end users. These can be the device manufacturer or a third-party service provider. M2M service provider itself, who provides the key M2M services to be used by all sorts of application services. Network service provider, who provides underlying network connectivity and related services. And M2M end users, who use or consume the M2M application services or other services. Let's think about some general functionalities. These functionalities may be fully or partially implemented on the device management solution. There are different ways of thinking about the functionalities, but still, let's view them from the perspective of a device lifecycle shown here, starting from the pre-deployment phase to the decommission or retirement phase. Let's assume we, as an M2M service provider, have a number of devices, but we haven't deployed them yet. Thus, we're now in the pre-deployment phase, when we need to do some initial configurations on the devices, so that we can connect them securely later on. These configurations include putting security credentials and policies, creating some device metadata, and so on. After that, in the post-deployment phase, when an initial connection happens from the device to a DM service endpoint, we need to be able to remotely provision or re-provision devices, and to do the device onboarding in order to add them into a remote DM service endpoint to manipulate them as managed devices. These processes can be initiated from a device or from a remote server. Then, after we provisioned the devices, they are in normal operation phase or maintenance phase, when we may need to configure devices to dynamically change the credentials and to change some values of the device metadata. For example, often implemented in the proprietary solutions. Therefore, we often need some standard ways and technologies to accomplish some common tasks, such as using a communication protocol to handle interactions between DM entities, encoding the messages, and utilizing a data model, and applying a procedural flow for management operations. A DM standard can ensure interoperability and compatibility across platforms and conditions. It can also evolve independently from specific DM technologies. A DM standard defines the standard ways and technologies for DM purposes. There are some existing DM standards for mobile devices, network devices, and IoT. However, when it comes to the IoT, we need to make sure the protocols can work in some conditions, such as support for flexible deployments and scale, efficient communications and execution on constrained devices and networks, support for various security options, able to integrate into other DM solutions and technologies, as well as its applicability in a broad range of industry segments. Here, I'll introduce some typical device management standards. At first, let's look at the TR069 standard. TR069 is a technical specification that defines the CPE Wide Area Network Management Protocol called CWMP by the Broadband Forum. TR069 originally targeted the broadband market. It meets the management needs of Internet access devices, such as gateways, routers, femtocells, and LAN devices, generally called TR069 CPE. CWMP defines a mechanism that encompasses secure auto-configuration of a CPE and also incorporates other CPE management functions into a common framework. The first version of TR069 was published in 2004, and the current version 1.4 was published in 2014. CWMP provides some primary functionalities, such as auto-configuration and dynamic service provisioning, firmware image management, software module management, status and performance monitoring, and diagnostics. From the protocol architecture point of view, the CWMP protocol uses remote procedure call methods on top of HTTP or HTTPS and SOAP, a standard XML-based syntax used to encode remote procedure calls. CWMP uses HTTP and TLS to secure communications between a CPE and auto-configuration server, called ACS, for confidentiality and authentication. There are other specifications defined around TR069, such as data model of managed objects for network devices or services, where you can check the Broadband Forum website for more detail. OMA Device Management, or OMA DM, is device management protocol for mobile devices such as mobile phones and tablets. It defines various management procedures and the interface between the OMA DM server and the clients, which are managed devices. The first version of OMA DM dated back to 2003, and the current version is 2.0, published in 2016. The OMA DM is platform neutral, so it can run on many platforms, including the mobile device management solution on Windows 10. Compared with earlier versions, OMA DM 2.0 is significantly enhanced in terms of reduced complexity, enhanced interoperability, and cost efficiency. The primary functionalities of OMA DM include setting initial configuration information, for example, provisioning, installation and updates of persistent information, for example, firmware updates, retrieval of management information from devices, including the retrieval of diagnostic information from devices, and processing events and alarms generated by devices. OMA DM is transport agnostic and uses the data transport mechanisms over HTTP, web, SMS, etc. OMA DM 2.0 utilizes a RESTful HTTP-based architecture, providing a transaction model and a data model for manipulating so-called management objects, a set of entities that can be manipulated by management actions over the OMA DM protocol. OMA DM 2.0 is not backward compatible with OMA DM 1.x, but the management objects for OMA DM 1.x can still be used in OMA DM 2.0. We've seen that TR069 and OMA DM have target applications in Internet access devices and mobile devices. Although they may be used in IoT devices, like gateways in general, the features are heavyweight and cannot fit well the broad spectrum of IoT devices. Therefore, there are a couple of DM standards used in IoT or M2M, which are OMA LightweightM2M and M2M standards. They are comparatively new standards. OMA LightweightM and data transfer mechanism between device management entities. This service is provided by a message transfer protocol. These services provided by the message transfer protocols also helps create the value chain for IoT applications with the enablement for interoperability for data and networks. Now, let's see technically how the message transfer protocols can help with transfer messages in DM solutions. In this example, the DM entities such as the DM server and the managed devices A to D running the DM server and client software are connected to the communication networks. The DM solution will benefit from the required logical connections from the clients to the server, which are created by the message transfer protocols between them, no matter what the possible changes in physical connections will be. We have different options for message transfers. Using the generic HTTP protocol can do the job. However, the rich features provided by HTTP are not necessary, and they'll introduce overhead for message transfer and processing. Therefore, in many IoT or M2M use cases, lightweight message transfer protocols came into play. There are a few open lightweight message transfer protocols, and the typical ones include MQTT and CoAP. They have been adopted by most IoT or M2M device management standards and platforms, such as IoT platforms from Microsoft Azure, IBM Bluemix, and Amazon AWS. Both protocols have strong support from the open source community as well. Learning the basics of these protocols can help with understanding many device management systems for IoT. First, let's look at MQTT. MQTT stands for Message Queue Telemetry Transport, and it's a publish-subscribe messaging protocol, which was originally standardized by IBM and is now standardized by the OASIS Consortium, which is a nonprofit consortium for open standards for the information society. MQTT follows a client-server model, where the server is called broker, and the multiple clients represent IoT or M2M devices. Note that MQTT requires all clients to open TCP connections to the broker. It is called a publish-subscribe messaging protocol. As example, suppose we have 4 clients and 1 broker, where clients B to D want to retrieve the location information of client A, which, for example, represents a vehicle with a GPS sensor, regularly publishing longitude and latitude values to the central broker. Thus, clients B to D need to subscribe to the topic location, and client A needs to publish the location value to the central broker. Then, every time when client A publishes new location value to the broker will forward the value to all subscribed clients. With this publish-subscribe mechanism, the message transfers are possible between not only 2 devices, but also between 1 device and many other devices, or between many devices to 1 device. In order to make it more lightweight to fit into sensor network environments, where a TCP connection from clients to the broker is not always possible, and a more efficient communication protocol is required, the MQTT variant for sensor networks called MQTT-SN is available. Note that the architecture of MQTT may be different from the upper layer DM software services, because it doesn't matter too much, as DM services only need to have logical connections provided by the underlying MQTT protocol entities. Now, let's look at CoAP. CoAP stands for Constrained Application Protocol, standardized by the Internet Engineering Task Force, an international open community for Internet standards. CoAP is purposely designed for a constrained network, a paradigm that many IoT systems have, with low power, lossy characteristics and resource-constrained devices. CoAP endpoints can directly interoperate with each other on the Internet, or with HTTP and RESTful web services through CoAP proxies. CoAP also follows the client-server model, but CoAP is considered a one-to-one protocol, and the CoAP client communicates with the CoAP server through connectionless UDP diagrams. It is possible to run over TCP or SMS bearers as well. CoAP is essentially a web transfer protocol, where CoAP clients make GET, PUT, POST, or DELETE requests to and get responses from the CoAP server endpoints, similar to HTTP. A CoAP client can observe this challenge, let's determine the device management functions in the operations phase based on a real-world smart parking scenario. In this application, suppose there are wireless security camera deployed beside a vehicle and an occupancy sensor mounted on the ground of a parking spot, and there are many other cameras and occupancy sensors deployed across citywide parking lots to monitor the parking spots and on-site traffic. Assuming both occupancy sensors and the security cameras can wirelessly interact with a remote DM server across the city, and the occupancy sensors are battery-powered with constrained resources, but the security cameras are mains-powered. Let's determine the general DM functionality for these two types of devices. You can try to list the functions for each type of devices in the table. I'm assuming this will take around 5 minutes to think about. In this table, the general DM functions in the operations phase are briefly listed on the very left column. The first function, device configuration, can be available on both types of devices. For example, during the normal operations, we would need to configure the device for the metadata or profiles. The firmware update function is likely to happen at times on the security cameras for security and feature upgrades due to the constrained resources such as power supply on the occupancy sensors. The occupancy detection feature is straightforward and relatively stable after deployment. This functionality is not likely to occur on them. Lastly, both devices will need to keep track of event alerts or logs. For example, the occupancy sensor needs to send occupancy events to the remote DM server, and the security camera would send the security alerts to the DM server. Also, both devices would need to send diagnostic information such as machine states over time to the DM server. For machine-to-machine communication and IoT, it's developed by the Open Mobile Alliance, primarily designed for resource-constrained M2M devices. The protocol defines the data model and the data encoding formats, communication mechanisms, security mechanisms for device management and remote control, and data collection without the need for complex computing and the UI operations. It uses the application layer CoAP protocol for message transfers. The communication security mechanism is based on the datagram transport layer security, called DTLS. Lightweight M2M has many use cases in different industry segments. One example is firmware update for a large number of smart streetlights, which are equipped with low-cost controllers often deployed in a city. In addition, it can be used in other applications, such as asset management for cars, where a car is connected to an M2M service to regularly report information data, where its owner can locate the car when it's stolen. Let's go back to the high-level components of lightweight M2M protocol, where there are two essential entities, lightweight M2M server and the lightweight M2M client. Lightweight M2M server is the logical component residing within M2M service or network provider, serving as an endpoint of the lightweight M2M protocol. The M2M applications can evoke the functions from the server. Lightweight M2M client is the logical component residing in a physical M2M device. One or multiple lightweight M2M servers may deal with multiple lightweight M2M clients, where each client contains multiple resource objects to be managed. How the lightweight M2M server interacts with the clients is defined in the four logical interfaces, which are Bootstrap, client registration, device management, and service enablement and information reporting. To have a clear picture of the lightweight M2M deployment, let's see the relationship of these two entities together with additional entities such as M2M service provider, network service providers network, M2M application service provider, and M2M end users. The network service provider provides the network communication services between the lightweight M2M clients and the lightweight M2M servers. An M2M service provider, shown here, owns both the lightweight M2M server and application, where the lightweight M2M server may connect to multiple clients. M2M end users can get M2M services by connecting the M2M service provider. Depending on the scope of the M2M service provider, the lightweight M2M server may reside within the network service provider's network, where the M2M service provider owns the M2M application services. It is possible that there are multiple servers existing in the system. In this example, the lightweight M2M clients shown on the left may interact with the intermediate server, which can be within another M2M or network service provider and with the remote lightweight M2M server from an M2M service provider. In order to make the intermediate server providers to connect to the M2M service provider on the right, it needs to have a lightweight M2M client inside of it. The management data on the lightweight M2M clients are in the form of objects and resources. Resource is a piece of information made available by the lightweight M2M client. The resource model in lightweight M2M defines how the resources are organized. Here, we can see that resources are logically organized into objects, where one lightweight M2M client may have multiple objects. Each object or resource has a unique identifier. The structural relationship between the lightweight M2M client, its objects, and the resources can be seen in this diagram. The remaining commonly used objects and resources are already defined by OMA and other third parties, so you may easily find and reuse an existing one for an OMA solution. Since the lightweight M2M involves multiple protocols, let's see the block diagram of the protocol stack, where the lightweight M2M protocol endpoints on clients and servers need to run. In this diagram, we can see the application layer protocol CoAP uses the UDP and SMS bearers and the transport layer. The lightweight M2M protocol utilizes DTLS-based security with UDP and SMS bindings for meeting the communication security goals, such as authentication, confidentiality, and data integrity. The lower layer security can be used as alternative. Basically, lightweight M2M clients require credentials to securely communicate with lightweight M2M servers. Lightweight M2M protocol recommends that all communications between lightweight M2M clients and the servers are authenticated using mutual authentication. We need to do two things first: modeling the device resources and making the device resource uniquely identifiable in order to access them. By the lightweight M2M standard, a resource is defined as a piece of information made available by the lightweight M2M client. Multiple resources are logically organized into objects. The diagram shown on the left indicates the logical relationship between resource, object, and the lightweight M2M client, where each client may have multiple objects and each object has one or more resources. The operation of a resource can be a combination of read or write. For example, the read operation is on the value as a resource, such as sensor value or firmware version. The read and the write operation of a resource can be the device location, which needs to be read and updated as the location of device might change. The execute operation is used for executable resources and exclusively regarding the other operations. An example of such resource is the firmware update resource, where it has an empty value and can be addressed by a lightweight M2M server to trigger a firmware update action in the client. An object must firstly be instantiated for the lightweight M2M client. An instantiated object is called object instance. Now, let's look at how to make the device data uniquely identifiable. An object is defined by several attributes. In addition to the object name and unique object ID, the instances attribute mean if the object can have multiple instances or just a single instance. The mandatory attribute means if the object is mandatory or optional to be contained in the client. The object URN attribute specifies the unique uniform resource name of the object following the format. In the first bracket, the OMA label means the objects are defined by OMA. The EXT means the object is defined by a third-party standards development organization. The X label means the object is defined by a company or individual. Object version is optionally used in case an object may evolve into different versions over time. Let's see three typical examples. The first example is for a standard firmware update object defined by the OMA LightweightM2M Standard. The second example is the temperature sensor object defined by the IPSO Alliance with the label EXT followed by the object ID 3303. The third example is the host device information object defined by AT&T, describing any device with a cellular module that can be queried by the lightweight M2M server. The object URN has the label X, followed by the object ID 10241. Now, we can uniquely identify an object. Identifying an object instance or a resource becomes easy, as we just to keep the ID of an object instance and object-specific resource unique within a specific object. If we follow along the resource model we've just mentioned, we can identify the resource number 1 under the first instance of the object with ID 0 as /3/0/1. Now, to strengthen our understanding of the lightweight M2M resource model, let's see a couple of more examples. There are several objects defined by the lightweight M2M standard, which are security object, server object, access control object, device object, connectivity monitoring object, firmware update object, location object, and connectivity stats object. All objects and resources can be checked from the lightweight M2M registry website, as shown here. From this page, we can see that the object ID linked to the XML file, name, description, as well as the lightweight M2M specifications, which defines the object. You can also use the Eclipse virtual link to generate object-related codes for different platforms. For example, we can generate a Java code for this firmware update object to be used in Eclipse Leshan for sending and receiving lightweight M2M messages to and from the lightweight M2M server by just clicking this button. Every object here is defined with several essential fields followed by the resources. If we take a look at the firmware update object, we can see that we have 7 fields defined for this object. They are the object name, object ID, object version, object URN, instances, lightweight M2M version, and mandatory option. Every object has an object name and object ID as its unique identifier. Object IDs of standard lightweight M2M objects are assigned and maintained by the OMA naming authority. The instances field indicate whether its object supports multiple object instances or not. If this field is multiple, then the number of object instances can be from 0 to many. If this field is single, then the number of object instances can be from 0 to 1. Similarly, if the object field is mandatory, and object field instance is single, then the number of the object instance must be 1. To have a clear picture of what the definition the lightweight M2M server and lightweight M2M client. They use 4 logical interfaces to standardize the way of performing device management interactions between them. The 4 interfaces are called Bootstrap, client registration, device management and service enablement, and information reporting. The arrows in this diagram indicate the entities offering or exposing interfaces, not the directions of the communications. The Bootstrap interface is used for the lightweight M2M server to provision essential information into the lightweight M2M client to enable the client to perform the operation register with 1 or more servers. There are 4 Bootstrap modes providing flexible ways of provisioning the devices. The factory mode means the Bootstrap information is configured before the deployment of the device. In the Bootstrap from Smart Card mode, the Bootstrap information can be done using a smart card connected to the lightweight M2M device, where a secure channel should be established between the smart card and the device. The Bootstrap sequence can also be initiated by the lightweight M2M client or the server. When doing this, we need the so-called lightweight M2M Bootstrap server entity to help connect the lightweight M2M client to the servers. In this case, the client must be pre-provisioned to have the Bootstrap server account in order to be able to establish a secure DTLS connection to the Bootstrap server. The client-initiated Bootstrap mode is used when the lightweight M2M server is not configured within the lightweight M2M client, or attempts to perform the register operation with lightweight M2M servers have failed. When we want to do the Bootstrap without the client sending the initial requests, we can use the server-initiated Bootstrap mode, where the lightweight M2M Bootstrap server will basically follow the similar steps in the client-initiated mode. The only difference is the Bootstrap server needs to know the client is ready for bootstrapping. These can be done easily, for example, when a device successfully connects to the network. The client registration interface is used to register with 1 or more lightweight M2M servers, remotely access and manage the client, and deregister from the server. Therefore, there are 3 corresponding operations associated with registration interface. There are register operation, update operation, and deregister operation. Let's see the example register operation. First, the client sends the request with some information, like endpoint name, registration lifetime, binding modes supported, the list of objects, and available object instances in the client. In this example, the endpoint and object instance IDs are shown. This way, the server then is able to identify object instances from the client. When the registration is done, the server will return with the COAP response code indicating the success of a registration procedure. The registration has a lifetime indicated by the lifetime resource and existing object instances in the lightweight M2M client. The update operation can be performed by the lightweight M2M client to update its registration information to the server registered. When the registration expires, without receiving an update from the client, the lightweight M2M server will remove the registration information of the client, and the client has to re-register to the server again. To avoid this to happen, the client can perform periodic update operations to refresh the registration status on the server. Here, we can see that this update operation is initiated by the client, and the server responses with the CoAP response code indicating the success of this operation. Alternatively, the client can send update operation to change the lifetime of the registration. In this example, the lifetime with the value 1000 seconds is sent as a parameter with the update operation. The deregister operation should be sent by the client when it no longer uses the lightweight M2M server or the server is shutting down. The server removes the registration information upon the reception of this message. The device management and service enablement interface is used by the server to access resources available from a client using create, read, write, delete, or execute operations. In this example, we show the essential operations in one diagram. The create operation here is used by the lightweight M2M server to create firmware object instance with the identifier /5/1 within the lightweight M2M client. The write operation here is used to change the value of the firmware URI resource with the identifier /5/1/1. This operation can also be used to change the value of multiple resources and the resource instances. The read operation here is used to access the value of the resource /5/1/1 we just wrote, i.e. the firmware URI. In addition, it can be used to access the value of an array of resource instances, an object instance, or odd instances of an object. The execute operation is used by the lightweight M2M server to initiate some actions on individual resource /5/1/2, i.e. the update resource of the firmware update object. In addition, there are discover operation and delete operations, which are used to discover the attributes attached to an object, object instances, and resources, and to delete an object instance in the LW M2M client. The information reporting interface is include the authorization, authentication, confidentiality, and data integrity for the communication between lightweight M2M entities. From the perspective of lightweight M2M protocol stack, DTLS provides the main security mechanism and the transport layer for the upper layer communication protocol, CoAP, although the SMS channel security can be used if a device uses a smart card. Note that in order to use the security features, lightweight M2M clients need to have the credentials and configuration information for secure communications with lightweight M2M servers through a bootstrapping process. Now, let's see the essential security features. Generally, authorization is used to determine after authentication which servers can do what with the client's resources and is implemented by the access control policies. An authorization process here is required when lightweight M2M servers need to be authorized to access object instances and resources within the lightweight M2M client. This is provided through the access control object instances within the lightweight M2M client. Authorization is used to determine here if a lightweight M2M server is authorized to instantiate a supported object in the lightweight M2M client, and to determine who the access control owner of that object instance is, and which access rights have been granted to lightweight M2M servers. Authentication of communicating lightweight M2M entities means that all communications between clients and servers, or bootstrap servers, are authenticated using mutual authentication. Confidentiality and data integrity of information between communicating lightweight M2M entities means that all communications between clients and servers, or bootstrap servers, are encrypted and integrity protected. DTLS 1.2 protocol is used in the lightweight M2M for secure data communications between the lightweight M2M client and lightweight M2M server, providing the secure handshaking, mutual authentication, data integrity, and the data encryption features. There are 3 types of credentials supported, which are pre-shared secrets, raw public keys, and certificates. To use these credentials, we need to use the security object, which is specified by the lightweight M2M standard. In order to enable the pre-shared key mode, we need to set some values to the mandatory resources of the security object instance. The security mode resource should be set to 0. The public key or identity resource must be used to store the pre-shared key identity. The secret key resource must be used to store the pre-shared key itself. When using raw public key mode, we need to set some different values here. The security mode resource must be set to 1. The public key or identity resource must be used to store the raw public key of the DTLS client. The secret key resource must be used to store the private key of the DTLS client. And the server public key resource must be used to store the raw public key of the DTLS server. In the certificate mode, we need to set the values of the security object resources differently. The security mode resource must be set to 2. The public key or identity resource must be used to store can be used to develop a lightweight M2M solution. Currently, it supports essential lightweight M2M implementations, such as server and client, access control, connectivity, firmware update, location, connectivity monitoring and stats, and DTLS-based security. Now, let's begin by building your lightweight M2M solution with LeShan. You'll use the access files for this chapter. Open the terminal, copy your access files directory, LeShan example, to your documents directory, and navigate to that directory, as shown here. Then, build the entire project directory by executing this command at your terminal prompt. It might take a few minutes to compile for the first time. After you compile the project, let's run the demo server and the demo client application you just built. Let's start running the demo server app first by executing the following command at your terminal. Now, your server app should be up and running. To check that, open your web browser at localhost 8080. You will see the web interface of this demo server. After we run the demo client, we should see the client and its resources. Now, let's run the demo client application in a new terminal window. After that, check the web interface we just opened, and your host running the demo client application is listed as a client endpoint, where the name is the host name of your computer by default. If you check the client endpoint name, we can see a list of resources associated to this device. In this interface, we can observe the resources, write and read values of them. If we scroll down to the bottom of the web page and click Observe for the temperature resource, we can see the live values sent from the demo client. That's the working demo of a LeShan lightweight M2M solution. Now, let's extend the example by building a custom application with Eclipse. Suppose our Eclipse workspace directory is set by default to this one. And then we copy the workspace directory and start Eclipse. Before we use Eclipse for the LeShan application project, we need to add the Maven-related Java class path variable to Eclipse. You can do it manually, but here we'll do it by executing the command at your terminal prompt. Run this command to generate Eclipse configuration files in order to make the project work with Eclipse. Now we're set up. We can now export the LeShan project and compile it with Eclipse. Let's look at the source code file, LeShan client demo.java, to see how the lightweight M2M client works, and then we'll modify code to add another resource. To start client instance, in the create and the start client function, the program first initializes the lightweight M2M objects, which include the custom object model defined in the 3303.xml file, as well as other default models, such as security, server, device, and location. Then, the custom temperature sensor needs to be added to the lightweight M2M object list with the ID following the lightweight M2M object and the resource registry published by OMA. After that, we can start the lightweight M2M client by invoking the client.start function. In order to understand how to define your objects, let's take a look at an example temperature sensor object using this demo. Open the file Visual Eclipse named 3303.xml, where you'll see some key info such as object ID and lightweight M2M resource identified by different resource IDs such as 5700, and you can refer to the lightweight M2M registry website you just saw to find IDs or other available resources commonly seen on IoT devices. Or you can define your own with OMA naming authority. However, to make this temperature sensor object work, you'll need to set an instance class to it. In this case, the class is defined in the source code named randomTemperatureSensor.java, right here, where the random temperature sensor class is inherited from the base instance enabler class, and it defines the functions to respond to the standard read, write, and execute operations on a resource. Similarly, we can extend this demo to add support of accelerometer sensor, which is defined in the source code file randomaccelerometersensor.java. Now we run the Leshan demo client 2 program in Eclipse. We'll In this challenge, we'll add an LWM2M humidity object instance to the Leshan application. You can try this based on the sample application in the exercise files directory for this chapter. I'm assuming this may take about 15 minutes to do. To solve this challenge, we'll first need to find the resource ID and the definition of an LWM2M humidity object. Since it is a registered object, we can find the information on the LWM2M object and the resource registry portal. Then, what we need is the XML file for the humidity object entry. Let's click the first link, showing the resource ID 3304, and download the content as the XML file into the resource subdirectory of the client demo application used for this chapter. Here, I'm downloading the 1.0 version in order to be compatible with the Leshan version I'm using. Then, we can put the XML file to the resource models subdirectory under the client demo application folder, and let's go ahead modifying the demo client application. Now, let's open the source code for the client demo application with a text editor such as Eclipse. Open the source file, Leshan client demo.java, and then add the XML file we just saved to the model path definition in this line. And define the object ID of this humidity sensor by adding another line here. Now we can scroll down and create instances which will be available at the startup for the humidity object. We can add the following line as shown here, where you can implement it in different ways, such as interacting with a specific humidity sensor and get data or outputting some simulated humidity values, where the random temperature sensor enabler class defined for the temperature sensor in the demo application is a good example. Now, we just refer to the existing random temperature sensor class and add our own humidity sensor enabler class here, where we output some simulated humidity readings similar to that defined in the random temperature sensor class. Then, we'll add the object ID of the humidity sensor to the LWM2M object enablers initializer in the Leshan client demo.java source file. Now, let's simply build the Maven project from the command line. After it's done, let's restart our demo server application in the client application. And then go back standardized by OMA, which is a global organization for M2M in IoT technologies, founded in 2012. The OMA organization consists of the main standards development organizations, industry consortia, and industry players around the world, including Broadband Forum and OMA we mentioned. The OMA standard is a set of technical specifications. The first release of OMA specifications was published in 2015, and the second release was published in 2016, while the next release is a work in progress. The OMA standard provides a framework to support a wide range of end-to-end IoT applications and services in various vertical applications. The OMA standard provides an interworking framework that can make devices or systems running different protocols work together, where the communication mechanism and data model and semantics in the OMA are separated to map to a specific external protocol. To solve the challenge of heterogeneity and interoperability between IoT systems, at a high level, OMA defines a horizontal architecture across heterogeneous platforms that can interoperate with each other. OMA abstracts the end-to-end M2M services into a layered model consisting of 3 layers. The application layer here consists of OMA applications and related business and operational logic. The common services layer consists of OMA service functions that enable OMA applications, including the device management and other services, service discovery, and policy enforcement. The network services layer provides transport, connection, and service functions. In a real-world M2M system, these layers can also be mapped to the services provided by the key actors and the stakeholders who provide application services, core M2M services, and network services. Based on this model, we can see the high-level security risks in terms of the point of attacks on the OMA-based system. In this diagram, the security attacks can occur on the internal interfaces between these layers on a generic OMA node. For example, a OMA-enabled gateway or a server. The security attacks can occur on the communication interfaces between these entities as well. The OMA standard defines a security framework to resolve these risks. Note that OMA doesn't define everything for IoT, but the common architecture and frameworks, data model, and functions above the transport layer where some existing network services and protocols need to be utilized. In this sense, the current OMA standard defines the protocol binding specifications. Let's check the OMA functional components and their relationships in detail in the OMA functional architecture. There are 3 entities defined by the OMA standard: application entity, common services entity, and network services entity. Every end-to-end OMA application or service can be deployed into infrastructure domain, representing the domain where the service providers providing a set of remote application or management services, and into field domain, representing the domain containing OMA devices deployed in the field. An application entity is an entity in the application layer that implements an M2M application service logic. For example, an application entity can be the instance of a remote temperature monitoring application, fleet tracking application, or lighting control application. Each application entity is identified by a unique ID. A common services entity represents an instantiation of a set of common service functions of the M2M environments, which are exposed to other entities through the MCA and MCC reference points. Examples of such services include device management and location services. A common services entity can interact with other common services entities in another infrastructure domain. A network services entity provides services from the underlying networks to the common services entities. Since there's information exchange between the entities, the reference points are defined, where one reference point contains one or more interfaces of any kind. The main reference points used between entities in the OMA system are shown here. Communication flows between an application entity and a common services entity cross the MCA reference point. Communication flows between 2 common services entities cross the MCC reference point. These flows enable a common services entity to use the services supported by another common services entity. Communication flows between a common services entity and the network services entity cross the MCN reference point. These flows enable a common services entity to use the supported services provided by the network services entity other than the transport and connectivity services. Communication flows between two common services entities in infrastructure nodes that are one M2M compliant and reside in different M2M services provider domains across the MCC apostrophe reference points. These three entities fit into the general actors in a one M2M based solution, where each domain contains one or more entities. The application service provider here provides and operates an M2M application. The M2M service provider provides applications to the application service provider and operates common services of M2M. The network service provider provides connectivity and services to the M2M as well as operations on the underlying network. Finally, there are end users who use the one M2M solution following the architecture shown here. To see a detailed deployment configuration based on aforementioned functional architecture, let's learn the one M2M nodes first, where physical objects or devices in an IoT system can be abstracted into different types of nodes, deployed into either the infrastructure domain or field domain. Nodes are defined as the logical entities that are individually identifiable in the one M2M system. In general, there are two kinds of nodes, CSE-capable nodes and non-CSE-capable nodes. A CSE-capable node is a logical entity containing at least one M2M CSE and 0 or more one M2M AEs. The application service node, infrastructure node, and the middle node are examples of CSE-capable nodes. A non-CSE-capable node doesn't contain any one M2M CSE or AEs. The application dedicated node and non-one M2M node are examples of non-CSE-capable nodes. With these one M2M nodes in mind, we can construct an one M2M system configuration shown in this diagram in one M2M terminology. First, we can separate the one M2M system into two domains, as we mentioned before. One is infrastructure domain, consisting of infrastructure nodes, and the other is field domain, containing other kinds of one M2M nodes. And we also depict some of the key actors of the one M2M system here. Having this in mind, let's see how these nodes deployed in these two domains interact with each other. The infrastructure node shown here at the top, containing one common services entity and 0 or multiple application entities. Usually, there's one infrastructure node per one M2M service provider. It communicates with another infrastructure node via the MCC apostrophe reference point. The application service node, ASN, is a node that contains one common services entity and at least one application entity. There may be 0 or more application service nodes in the field domain. The common services entity of the application service node communicates with another common services entity residing in a middle node or infrastructure node via the MCC reference point. The MCA reference point is used for the communication between its internal application entity and its internal common services entities. The application dedicated node, ADN, is a node that contains no common services entity and at least one application entity. In the field domain, there are 0 or more application dedicated nodes. An application entity in the application dedicated node communicates via the MCA reference point with a common services entity in the infrastructure node. Three essential one M2M entities are mapped to three layers. The device management is supported in a common services entity in the form of common services functions called CSFs. A CSF is an informative architecture construct which conceptually groups a number of sub-functions. One M2M specifies several common services functions as shown here. A common services entity instance can contain a subset of these common services functions. Now, we're focusing on the device management common services function. The device management common services function provides device management capabilities on middle nodes. For example, M2M gateways, application service nodes, for example, M2M devices, and application dedicated nodes, for example, constrained M2M devices, as well as devices within an M2M area network, which is, in one M2M context, an area network consisting of multiple application dedicated nodes and other types of nodes. Device Management Common Services Function, or DMG for short, provides a way for application entities to have device management capabilities on the one M2M nodes, without the knowledge of any specific protocols or data models. To understand how all this works, let's explore the device management architecture. In this diagram, we can see that the one M2M nodes involving in the device management are infrastructure node and the middle node, or application service node. The device management common services function residing in the two nodes can interact with each other through the MCC reference point shown in the middle, where the application entities may invoke the services provided by the device management common services function through the MCA reference points. This architecture allows the utilization of technology-specific protocols such as LightweightM2M, TR069, and OMA DM, etc. The adaptation and translation of the management-related requests from common services entities or application entities to the requests of the technology-specific protocols are done through the management adapter. In this diagram, the management adapter component within the DMG of the infrastructure node performs adaptation between the DMG and one or more management servers using the MS interface. The management adapter component in the DMG of the middle node or application service node performs translation and adaptation between the DMG and the management client using the LA interface. The MC interface used between the management server and the management client is dependent on the technology-specific protocol used. The roles of management adapters in the management server and the management client are different. The former does protocol translation between DMG and the management server, interaction with the management server selection, and discovery of technology-specific data model objects. The management adapter in the management client does two major things. At first, it discovers the technology-specific data model objects supported by the management client using the LA interface. Then, it creates a mapping between the data model objects to resources which can be used by the application entity in the infrastructure node to device management capabilities regarding the middle node or application service node. With device management architecture we've talked about, let's see how the management of an M2M device is done. We still follow the way of the one M2M system deployment, where the system is deployed into the infrastructure domain and the field domain. The field domain contains the one M2M nodes, such as middle nodes or application service nodes, that can connect to M2M devices in the M2M area networks. In order to manage managed devices are called device management entities. The example managed devices include regular or resource-constrained M2M devices, M2M gateways, and devices in an M2M area network. There are specific device management capabilities in terms of specific functions defined within the device management common services function. These functions include the device configuration function, which is used for configuring the capabilities of the managed devices. The device diagnostics and monitoring function, which includes the troubleshooting through the diagnostic tests and operational status or stats associated with the managed device. The device firmware management function, which provides the software lifecycle management for firmware components and artifacts for the managed devices. The device topology management function, which provides the management of the topology, transport protocol related, and device status information of the M2M area networks. Device management-related resources are implemented using the resource management mechanism defined by the one M2M standard, where any resource is modeled into an object. The common operations on resources include creation, retrieval, update, and deletion, called CRUD. However, the device management resources need to do something more, such as using a security mechanism of the management server to enable authorization and authentication for the access to the objects. The CRUD operations for device management resources can be done directly in IoT or M2M systems, there is a need for a security framework that can work across heterogeneous platforms and key common IoT or M2M elements, such as devices, gateways, and application endpoints. One M2M specifications include security frameworks to address these challenges. The high-level security services utilized by one M2M applications are from the security services layer, where these services can utilize the security-related APIs provided by lower-level modular security functions. This architecture allows the involvement and changes in specific features to be decoupled from the high-level security functions. The security environment abstraction layer provides access to the secure environments via security transport APIs, and the layer can be accessed from the security services layer. The security environment is a logical entity that provides sensitive functions operating on sensitive data, secure storage, and other resources or functions. The security services layer provides 5 essential services: access management, sensitive data handling, security association establishment, security administration, and identity protection. Let's see what these services are one by one. Access management has 3 components: authentication, authorization, and access control. Here is the general procedure of using those components. The M2M entities need to be mutually authenticated first. Then, the authorization component will authorize the services and the data access to authenticated entities through provisioned access control policies and assigned roles. The authorization procedure controls access to the resources and services hosted by common services entities and application entities. Sensitive data handling provides security storage for sensitive data, cryptographic operations, and methods for bootstrapping initial secrets. Data securely stored by the application entity or common services entity shall only be accessible through the security APIs by authorized entities. The sensitive data of a field domain can be determined by security risk analysis. Security association establishment provides secure connection via secure session establishment and via object security. A successful security association establishment results in a TLS or DTLS session, which can protect hop-by-hop message exchanges between application entities or common services entities. Such security association may be done differently depending on the M2M entities in the domain. For example, the security association establishment is mandatory between common services entities in the infrastructure domain, which it may not be required between common services entities and application entities, or common services entities in the field domain if the risk assessment result permits. Security administration provides the capability to manage the remote provisioning and security functions, resources, and attributes. These include management of sensitive data and the resources provided via the secure environment. Identity protection provides services to the application layer, such as pseudonyms and protecting the anonymity of transactions. To see how these work in action, let's take a look at each of these services from the 2 phases of the device lifecycle, where the provisioning and configuration need to be done in the deployment phase, and the security association establishment needs to be done in the operation phase. An M2M device needs provisioning and configuration from pre- and post-provisioning procedures. Pre-provisioning, for example, can be hard-coded credentials done during manufacturing or product development phase. Post-provisioning can be done through remote security provisioning before its actual operations, where an entity in the field domain needs to establish a secure association with an M2M service provider in the infrastructure domain. There are a few remote security provisioning frameworks defined, such as remote security provisioning frameworks based on pre-provisioned symmetric enrollee key, certificates, and generic bootstrapping architecture using the 3GPP GPA standard. These frameworks use the security and is an open source 1M2M based platform. OM2M supports the 1M2M nodes, such as infrastructure node, middle node, application node, and application dedicated node, as well as MCA and MCC reference points, TLS-based security, HTTP, and CoAP protocol bindings. The supported databases are SQL H2 and NoSQL. Through a reference point based on a RESTful API, a range of devices, applications, and services can be integrated. OM2M is running on top of an OSGI runtime, and the common services entities defined in M2M specifications need to be implemented as plugins. For example, the support for HTTP or CoAP binding is installed as a plugin. The support for device management protocols such as OMA DM and LightweightM2M needs to be supported in the form of a plugin as well. The support for interworking proxies for Zigbee, Notion, or Z-Wave standards need to be installed as plugins. Now, let's see how to build the OM2M demo. Note that we need the Maven and the Java SDK 1.7 or later to run the demo. Go to the exercise file directory for this chapter in your command line. Then, go to the OM2M example directory and compile the project by executing the command. After the compilation, we'll start the infrastructure common services entity demo first, and then the middle node common service entity demo later in the command line. First, we start the infrastructure common services entity OSGI console. To do that, we need to go to the directory first. Then, we start infrastructure common services entity by executing the start.sh file on Linux and Mac OS X, or start.bat on Windows. Next, the Equinox OSGI console will start with the infrastructure common services entity related plugins up and running on top of it. The common services entities are implemented as OSGI plugins called bundles. To see the full list of current OSGI bundles, type SS in the OSGI console here, where we can see the list of bundles with their IDs and the states. In OSGI environment, each bundle has 6 states in its lifecycle, where in this list, the bundles with active state mean they're up and running. The bundles with resolved state means they're either ready to run or stopped. Since there is an active web application bundle installed, we can browse the resources on a web interface. So let's go back to the web interface. Go to the URL http 127.0.0.1 at port 880/web page and type admin in the user and password field. Then we click the login button. After that, we'll see the list of infrastructure common services entity resources, where it lists the resources and their attributes. Under the ACP_admin resource, we can also see the access control attributes. Next, we'll start the middle node common services entity OSGI console. Similarly, go to the directory for the middle node common services entity under the OM2M example directory. And then execute a shell script named start.sh. Then if we go back to the web interface we just opened, we'll see the resources for the middle node common services entities. We may need to re-log in again. Now we can see the middle node common services entity is listed in the resource tree. And in this challenge, we're going to use a few REST APIs to create a simple custom application based on the OM2M REST API documentation. We'll need to make the infrastructure node CSE and the middle node CSE applications up and running in the exercise file using JDK 8. And we'll need a tool such as Postman to send the HTTP GET or POST requests. We'll need to complete the following tasks. First, we'll use the APIs to create our application named temp_sensor on the MNCSE entity. Then we'll need to add a data content instance resource with a sample value 25 degrees Celsius. You can refer to the demo requests on the REST API documentation. I'm assuming this challenge may take up to 30 minutes. To solve the challenge, we'll need to do a few steps. We'll run the InCSE and MNCSE applications first. Please make sure the OM2M example directory under the exercise files directory was compiled with Maven and JDK as shown here. Then we'll run the InCSE application and MNCSE application. Then, let's go to the web interface of the service. Once we ensure the services are up and running, we can open Postman to send our HTTP requests for creating an application, a data container resource, and a data content instance resource. Here, let's create our application first, using the HTTP post request with the URL, header, and body contents shown here. Now we can see the response from Postman, meaning the application was created successfully. Next, let's create a data container by sending another HTTP post request with the URL, header, and body contents shown here. And we can see the response from the MNCSE server. Finally, let's add the data content instance resource by sending an HTTP post. The fully managed cloud-hosted service on IBM Bluemix designed to simplify the IoT development, and it provides device management capabilities. With this platform, devices are classified as managed devices and unmanaged devices. The managed devices are able to interact with the IBM Watson IoT Platform device management services using the device management protocol, which is built on top of MQTT and HTTP. The managed devices can be remotely operated to do remote reboot, factory reset, and updates on firmware images, location, diagnostic information, etc. I'll show you how to use the Watson IoT Platform to do the firmware update. First, let's log into the IBM Watson IoT Platform portal and IBM Bluemix portal with your IBM Bluemix account, as we need to create the IoT Platform service and the database service outside the Watson IoT Platform portal, which can only be done through the Bluemix portal. To create a Watson IoT Platform service, we need to go to the Bluemix dashboard to do that. Here, there is no service available, so we need to create a service. And then, we scroll down to the Internet of Things and click the Internet of Things Platform menu. We give the service name as is. Make sure you have a space created under your organization. Then we click the Create button to create the Watson IoT Platform service. Then we hit the Launch button. Once the IoT Platform service is created, you can check that through the IBM Bluemix dashboard. And also, on your IBM Watson IoT Platform portal you opened, you can see your portal is created under the drop-down menu shown here. If you create multiple IoT Platform services, these drop-down menu will show multiple items. Here, we only create one platform service. If we click the menu item, we can see the Watson IoT Platform portal for us. Now, we're going to create a device. To do that, on the left pane, choose Devices. We have no devices listed or created, so we're going to create one. To do that, click the Add Device button. Since we don't have device type as well, let's create a device type first. We can name our device type like My Device Type 1, and then we can click Next. Here, we can choose some metadata fields, like firmware version, serial number, and descriptive location. Now we can put some values to those fields. For example, serial number we put 0001, firmware version we put 0.0.1. Descriptive location we can put my location. Now we can click the Create button to create the device type. Since we have the device type created, we can add a device based on the device type. Now we can click Next. We can type in the device ID. Here I use the ID My Device ID 001 and serial number 0001, firmware version the same as 0.0.1, and then we click Next and Next. In this step, we don't have to put anything because we want to use the auto-generated authentication token. So once the device is created, the authentication token will be created as well. Here's the overview of the device information we just put. Now we add the device. In this step, we make a note of the authentication token here because we'll use that later. You can copy all the information for this device here as well. Now we have the first device created. In this way, we finished registering an IoT device in the Watson IoT Platform. In a similar way, you can create more devices. However, we just use one device for demo purposes. Because we need to have a firmware repository set up on the cloud platform, we need to create a database service on the platform. To do this, we need to go back to the IBM Bluemix dashboard again, where we can see all the services list. So here, we're going to create another service for database. We're going to create a clouded NoSQL database service. So let's click this item. We can keep the service name as is. Now we create a database service. The new services should be listed under the Services tab. Since we have the database service set up, we need to create a firmware repo. In order to do that, let's click this service. And we can create a database by launching the service. So here is the interface. We can create a database. To do that, on the left pane, we click the database icon, and then we click the Create Database button. So here, we need to name the database into firmware_repository, and then we click Create. Now the database is created. We have to do one more thing. We have to create an entry in this database. An entry is called a document in this database. So we create a document here. We need to add another line here to indicate the version of the firmware repo, which should be higher than the firmware version of the device. Now we can create a document by clicking this button, and we can see the document created. But we have to do one more thing by adding an attachment to this document, which is the actual binary firmware object we're going to update to the device. So we can choose a file as the firmware object. We can use the example firmware object in your exercise file. And we can choose to upload this attachment to the database. Now, the firmware object is attached. Now we can save the changes. Okay, we have finished creating the actual document we're going to use later. So for the cloud and database service, we have to do one more thing. In order to make it remotely accessible, we have to create some credentials for the connection. Here we have no credentials created, so we need to create one. Let's hit the new credential button here, and we keep the credentials name as this, and we click Add button. Now, the credentials info was created successfully. We can see the actual values of the credential info. Now, we've almost finished setting up the database service for the firmware updates. Let's start building the simulated device app. Before we build app, we need to modify some configuration parameters in the configuration file. So go to the example files directory for this chapter and find the file called dmservice_sample.properties. Open the file with a text editor. You can see that there are several parameters we need to fit it in, including organization ID, device type, device ID, and the device token we just created, as well as some authentication information regarding the credential info of the database service. We can just copy those information from the Watson IoT Platform portal and the Bluemix portal to this configuration file. And then we put the database name for our firmware repo. Because we use the same name, so we don't have to change it. Now, we're going to create the connection stream for this parameter. We copy the username stream to this stream, and then we need the database name, and then the document ID and attachment name. So we have to go back to the Cloud and Database Service interface to check those values. This is document ID. This is the attachment name. Now, we save the file, and we're going to change some values here. To see the organization ID, let's go back the path to the two Java program files are shown here. One is for the server app, and the other is for the simulated device app. I also opened the two terminal windows. One is navigated to the directory to the server app, and the other is navigated to the directory of the simulated device app. The path to the two directories are shown here. Microsoft Azure IoT Hub is a fully managed service that enables reliable and secure bidirectional communications between millions of IoT devices and a solution backend. It provides device-to-cloud and cloud-to-device communication options, such as messaging, file transfer, and request-to-reply methods. It also provides authentication and secure connectivity, support for MQTT, HTTP, AMQP, and custom protocols, as well as SDKs. There are many things we can do with Azure IoT Hub, but let's focus on the device management here, with which you can remotely manage, configure, and update your devices. Specifically, we can use the Azure IoT Hub primitives, such as device twin and direct methods, where the direct methods are for communication between a device and the cloud service following a request-reply model, where a request gets a reply or response. For example, a direct method can be used to control a light, where the response needs to be returned in a timely manner. Direct methods are HTTP only from the cloud side and MQTT only from the device side. After logged into the Azure portal with your account, which you can freely register one with a trial subscription to Azure services. I'm using a trial account, which allows me to use some IoT Hub services. Now, let's create an IoT Hub first. Type the name Device Management here, where you can use any name you like. Choose to use the free F1 tier, which should be enough for our demo. Keep the default options in the following fields and create a new resource group named Resource Group 1. Choose Pin to Dashboard and then click the Create button. Then your IoT Hub will be deployed, which may take a few minutes. Next, we need to create a device identity because a device cannot connect to IoT Hub unless it has an entry in the identity registry on your IoT Hub. To do this, click the Device Management Azure IoT Hub we just created and go to your IoT Hub Lite. Then, click the Device Explorer menu and the button. Here, let's add a new device identity on this interface. Use the device ID myDevice001, as we will use it later, and use the default authentication type and leave the keys blank, as they will be automatically generated. Let's click Save button. Now, the device identity is created. Then, we'll see a new device entry is created with the keys generated. Here, let's copy and keep a note of the connection stream primary key here, as we will use it later in our demo. Let's go back to the Device Management IoT Hub blade, as you will need the same connection stream in order to connect your IoT Hub. Go to the Shared Access Policies blade under Settings, and click the IoT Hub Owner Policy. Copy and keep a note of the connection stream primary key here. Then go to the exercise files folder for this chapter, where we'll see two folders, one for simulated device app and the other for server app. Open the app.java file window for the simulated device application with the text editor and put your device connection stream here. Then you save the file and go to the app.java file for the server app. Similarly, paste your IoT Hub connection stream to your server program file here. Also, make sure your device ID stream has the value of myDevice001 we just created. Now, we can programmatically show the reboot and location update actions running the simulated device Java program. First, let's build and run it in the terminal. Go to the simulated device directory and execute the following maven commands to build your simulated device app at the terminal prompt. After that, let's run the program by executing the following command. Now, the simulated device app is up and running. Similarly, open the terminal window for the server app and compile the program for the server app. Then, let's run the program by executing the following command. Note that we added an option to pass the reboot argument into the app. This way, the server app will invoke the reboot direct method we defined and send it to the simulated device for local execution. You'll see the simulated reboot process is handled by the device app in a thread with the result outputs like rebooting and reboot done. You can extend this sample program to actually secure connection management and transfer of data from various devices. It also provides some essential IoT services, including device management and networking. Now let's see how to use the Google Cloud IoT for device management. First, let's go to the Cloud IoT Core portal. Then let's sign in our Google account. We can use the free trial service. Now we can create a new project and enable the APIs for Cloud IoT Core and the Cloud Pub and Sub. Now we'll need to install the Google Cloud SDK and use Google Cloud Shell. Google Cloud SDK provides tools to manage resources and applications hosted on Google Cloud. You can go to the Google Cloud SDK and get the download link for different operating system platforms. Here I'm installing the SDK on the Mac OS. You can follow the instructions on this page for the installation. Once you download the package, you can extract the package to any folder. Now I'm just extracting that to the downloads directory. And then we can execute the install.sh script for the installation. The installation is straightforward, and after it's done, you can perform the initial setups by running the command gcloud-init. The default configuration will be created and used as active configuration if you don't have any existing ones. Here I just go ahead with default configuration. Next, we'll need to select or create a project to work on. Here I just created a unique project named myproject97480 with the ID. You should take a note of the ID as well use it later. You can also create and view the project from your Google Cloud portal. Now that we've done Cloud SDK installation and the project setup, we can start adding a device to the registry. Let's go to the IoT Core portal first. And then we need to create a registry. So you can specify your registry ID as My Device Registry and select your region, for example, US Central 1, and then create a Cloud PubSub topic. Here I just choose the one I used, which is called My-Device-Events. Once it's done, you can see your device registry on this portal. Now let's create some certificate for device authentication in our terminal with the OpenSSL utility and issue the following command. After that, the public key and the private key files will be generated in our current directory. Then, we'll also need to download Google's CA root certificate from Google Trust Services into the same folder. These files will be used later. Now, let's go to the Google Cloud IoT portal to create a virtual device. Click Devices on the left pane and click Create a Device button at the top. Specify a device ID, such as My Device 1, and choose to allow the device communication. And in the authentication field, choose the public key format as RS-256-X509. And then upload the public key file called rsa_cert.pan. And then you can create the device by clicking the Create button. Now we can go back to the terminal and clone the Node.js samples from GitHub repo by executing the following command. Then let's go to the MQTT sample directory and let's go to the MQTT samples directory. And copy the Google CA root, certificate, and private key files into this directory. Once it's done, provides secure interactions from connected devices with cloud applications and other devices. AWS IoT provides various IoT services, such as IoT Core and IoT Device Management services. AWS IoT Device Management provides a registry for IoT devices, which can be physical or logical entities, such as application instances. Now, let's start with creating an IoT device registry in AWS IoT, and then see how to manage it. Once you log onto the AWS console portal, let's locate the IoT Device Management pane through the search bar. On the left side of the AWS IoT pane, let's click the Manage menu. Now, let's click Create button on the top right of the page. And then register an IoT device registry by clicking Create a single thing. Then we'll give it a name such as My Device. Please note that there is a device naming convention to follow from the AWS IoT documentation. We can create a type for this type of thing. For example, Smart Light I created before. Then we can add an attribute key, such as serial number with a sample value, such as SN123. Then we're going to create certificate, and we will store the device certificate, private key, and public key, as well as the root CA for AWS IoT to a secure place on our computer. But here, I just download them to the Downloads search directory for this demo only. I also renamed these files for easy reference later. Then we can click Activate and Done. Now the device registry is created, and we can check the details by clicking the device name listed here. We can also interact with the so-called device shadow to create, update, and delete shadows using MQTT, even if the device is not connected to the AWS IoT. Now, let's see how to connect to the device called My Device 1 I created before. First, let's install the AWS IoT SDK by issuing the following command to your terminal. Then, use it to clone the sample application repo. And then go to the samples application folder. The sample directory includes the applications that allowed us to subscribe to a topic, test topic, publishes 10 messages to that topic, and displays the messages as they are received from the message broker. Before running the script, let's make sure our things policy provides permissions for the sample script to connect, subscribe, publish, and receive. Before running the script, make sure our things policy provides permissions for the sample script to connect, subscribe, publish, and receive. The policy JSON is displayed in the following example. In this JSON file, we should replace the region and account streams with our AWS account and region. Then we'll need to attach the policy to the certificate that the device registry is used. Here, it is the certificate of My Device 1 I've created. Let's click the device name in the device list, and then click Certificates menu on the left pane. And besides the certificate we've created before, there's a drop-down menu that allows us to attach the policy we just created. Let's click the device name in the device list, and then click Security. And then click Certificate we've created before. And then we can see there's a drop-down menu that allows us to attach the policy we've created called My Policy. So if you check My Policy and Certificate, and you can see that the device certificate is now attached to that policy as well. Now, let's go back to the terminal and issue the command to run the sample script. We'll use the verbosity option to print out debug information. Note that the endpoint value of your device should be different from the one I'm using here, and this value can be easily found from the device details page under Interact. After running this script, we can see that the test messages were successfully updated to the MQTT test topic. We can also test the MQTT messages with the web-based MQTT test client. To do this, let's scroll down the left. Standards, technologies, tools, and the platforms surrounding the device management. I hope these will give you a good foundation for your device management solutions. For the next steps, you can build your device management solution with open source tools and examples, and with a commercial IoT platform we've covered. You can check the technical specifications of the device management related standards, such as OMA M2M and LightweightM2M for more details, or the latest developments as the technologies or standards may evolve over time. I encourage you to check out my other course on IoT Foundations, Low Power Wireless Networking. as well as the other IoT topics covered in the library. Feel free to explore other resources such as my blog or other technical articles.